afternoon, everyone. So it's a post-lunch session. I know it's very hot, so I try to make short and make it interesting as much as I can. So let's dive into the topic. So before going into the topic for today, I'd like to start with a small story. So in 1986, a crew of scientists were preparing for a safety test in one of the famous nuclear reactors. So the objective of the test is straightforward. So they wanted to bridge the time gap between the grid failure and the diesel power back generator to come alive. So especially they wanted to keep the coolant pump, which is one of the critical component in the nuclear reactor. So they wanted to keep it running all the time. So this is the objective. So when we have the grid power turns off, it has almost 60 to 70 seconds to wait for the diesel generator to turn on. So they wanted to keep the free running turbine power to feed back to the coolant pump in order to mitigate that time gap. The test looks simple, but it involves a lot of critical steps. So the very first step, what they did was turning off an emergency cooling system. So it is one of the critical safety net in the nuclear reactor in case of any failure or in case of any emergency mitigation. So initially the test was planned to be executed in the morning shift, but due to a lot of some non-technical hurdles, they have postponed the test to the night shift, keeping that safety net off for such a long time. So when the night shift took over, they have very less number of scientists and under pressure and with less experience. Still, they wanted to continue the test and complete it before the next shift takeover. So they started making decisions wrong one by one without realizing the mistakes. So even they have violated a lot of safety protocols, and even a lot of safety alarms have been ignored, assuming that it is common in such safety test scenario. So at the end, out of control, the reactor becomes so hot and it becomes exploded due to the hydrogen generation. Because of that, the radioactive has been leaked to the environment, leading to a disaster. So it became one of the darkest history of running the nuclear reactors. So the incident is nothing other than the Chernobyl incident, which is caused due to the reduced power operation. It has been reduced by the operators and turning off the emergency cooling system and removal of the control rod to the unsafe height. So the consequences are generation of hydrogen gas and leads to an explosion and radioactive decay to the environment. So the later investigation indicated that it is due to the series of human mistakes and the instrumentation faults has been the major cause of this particular incident. So now imagine we have an AI technology back then, a predictive model could have forecasted an unsafe operating conditions, or a simple anomaly detection model could have highlighted an unusual pattern. Then the history could have been different, and we may not be talking about this incident today. Actually speaking, they wanted to improve the performance or improve the safety of the reactors. So running safety experiments is really hard. Actually, it is not, at least now. So I'm Muthu Kumar. I'm currently working in Indira Gandhi Atomic Research Center, focusing on AI-driven solutions for enhancing the safety of the nuclear reactors. So we do also run a lot of safety experiments. So what are the ways that we can do that instead of running directly on the nuclear reactor? What are the other solutions to do that? The very first way is developing a physical model of the real component or the real system. So what is meant by a physical model? If you assume, or let's take an example of a motor can be represented as a mathematical equation of resistance and inductance. So we can simulate the exact functionality of a motor with the equivalent circuit. So we have a real asset, and we can develop a physical model using a lot of mathematical equations and the physics-based models. So instead of running our tests directly on the real asset, we can run our test conditions directly to the physical model, and we can analyze the results. But will that be a foolproof? Not really, because the physical model will be having a lot of assumptions about the real system. So if we want some outputs which has to be exactly similar to the real asset, then those assumptions has to be eliminated. So the very first step, what we did was connecting a line directly from the real asset to the physical model through sensor data. So with this, what the physical model sees is it can understand the real operating conditions or the real environmental conditions of the real asset, and it can take that as a blueprint, and we can run the safety test or test conditions on top of it. So it helps to reduce the assumptions but does not fully reduce it. So this particular concept is called digital twin and has been used predominantly in the industrial systems right now. So now it has been seen as an open loop, but we can extend this functionality to a closed loop so that we can have an additional functionality in top of this particular digital twin. So with the real computation power, the complex computation power that we have right now in our hand, what we can do is, let's say if an operator wants to change a parameter, for example, changing the flow rate from certain 1000 tons per hour to some 500 tons per hour, instead of running that particular change directly on the reactor, he can run it directly on the physical model. He can see the performance, and that model will update the parameters back to the real set if it does not forecast any failures or does not forecast any anomalies. Whereas if it rise any anomalies, a human in the loop will be notified or warned that there will be some problem with that particular parameter change. So this is the actions to the plant. This complete cycle has been called as a digital twin, and we are currently using that digital twin concept to run our safety experiments. But where is AI involved here? So that's a concept. It just takes in the sensor data and performs an analysis and then updates it back to the plant. So with the help of AI, we can improve the performance of the digital twin to the next level. So let's take an example of estimating the temperature of the physical asset. So basically, it can be estimated based on this mathematical equation. So the mathematical equation does not consider any unexpected wear or any anomalies. It just considers the time over which the system is going to be run. So there will be always an error associated with it when we run any system. So we wanted to eliminate this error. This error actually happens because of the lot of assumptions still we have in our model, even after having the digital twin. So what we can do is, since we have a historical data, since we are running our nuclear reactor for such a long time, we'll be having almost 10 to 15 years of data in our hand. If we can able to develop a data model that can exactly simulate each and every component inside the real system, then we can feed the sensor data, the supervised sensor data to the data model, and it can able to predict the errors. So this kind of modeling is called residual modeling. So with this technique, we can able to eliminate the error to the maximum extent. So with this, we can eliminate the assumptions as well. So instead of a digital twin only with a physical model, we can side by side, we can have a data model for each component that interfaces and averages out the errors between the physical and the data model. So the data model that we have prepared can also be extended for other purposes. So this is one of the machine health profile. So the machine starts to deteriorate over the period of time, but not all the machines, or even the same machine with a different unit does not follow the same profile. We do not know, because it may be operating under different operating conditions, different environmental conditions, different parameters. So we cannot able to estimate the healthiness of the system. So that's why we used to have a periodic maintenance schedule for most of the components that we have. So if the periodic maintenance would be sufficient for any system, then we would have not seen any failures due to the instrumentation or the component failure. But we are still having a lot of failure which is happening because of the faults. So we need to go beyond the periodic maintenance schedule and find an alternative way. So for that purpose, we have used a technique called remaining useful life estimation. So what does it mean? Let's say if I have a component which has been running for almost 5 years, I can estimate the remaining useful life that the component can run without failure. So that time difference we calculate as an absolute value. It may be in days or in weeks or in months even. So what is the importance? So it is very much important for two reasons. One is for the unexpected weird or anomalies which happens, which will not be captured by the regular time-based deterioration profile. And the another design constraint is specifically for our purpose, like nuclear reactor purpose. Let's say we have different components, state or the condition of each component are estimated based on its feedback from the component alone. For example, if I press a button to turn on a light, then we'll take the feedback from the light whether the light has been turned on. So this is how we complete the loop. So, but here in a safety critical environment, we cannot have any design constraints or design errors. We should eliminate the design errors, design constraints at the very early stage. So for that purpose, for example, if you take an example of a 3-mile incident in nuclear reactor in the US, which has been triggered by a simple stuck open failure of a valve. It's a very common failure, how that has been overlooked. When the later investigation indicated that it already had a self-check mechanism has been routed to the control room. But it was how it was missed. When they go for a deeper investigation, they identified that it was a design problem of the control valve itself. The control valve feedback does not comes from the real state of the control valve, whereas it was from the control input. So the control input is trying to change the state of the valve, whereas the valve is not changing its state. So since we are depending only on the feedback for that particular component alone, we will be ending up with such problems. So if we have a data model, the data model does not see the condition of that component alone, whereas we can estimate the functioning of the particular component based on the overall system behavior. So for these two purposes, we can have the data model that can able to predict the remaining useful life. So REL estimation, we try with different techniques and then we end up with doing with machine learning algorithms. But here, this particular problem comes under a supervised learning problem. So we need to have a lot of data associated with the failure. Since it's a critical component, we may not be running our system to fail so that we can record the data. So for this purpose, we used our digital twin, whatever we have prepared, and that digital twin will generate the data with the failure information. So all other steps is going to be same as such in other industries, whatever they are following for any other machine learning algorithms. For example, data pre-processing or model development, evaluation, and then retrain based on the validation result is not satisfied, and then the deployment. So the deployment also has a different strategy for this particular safety critical environment that we'll be seeing. So before going to next topic, I would like to explore what is the nuclear program of India and what Indira Gandhi Atomic Center is working on. So the nuclear program of India has been divided into 3 stages. So in the stage 1, we used to have a pressurized heavy water reactor that takes in a natural uranium as fuel and it generates energy. But the problem with this particular reactor is it has been, the efficiency of this particular reactor is lesser than 10%, which means the fuel which has been burnt in the PSWR are having still a lot of potential to generate more energy. So, and then the PSWR has been, we are deploying the PSWR in different places with the help of other countries. So that's where the second stage, the Indira Gandhi Atomic Research Center have been working on, the fast breeder reactors. So it takes the used fuel directly from the first stage reactor and has been fed to the fast breeder reactor. It generates energy. Along with that, it generates fuel as well. So the advantage of this particular reactor is we do not need to depend on any other countries as we do not have an enrichment facility available. So the output of this particular reactor has been given to another reactor that also been feeding to can be used in the another reactor as a fuel directly without any pre-processing. So why we are talking about this? So in the fast breeder reactor, we can assume a reactor as a two-stage device. It will be having the heat generation and the heat removal. The heat generation part has been taken care with the fuel with the fission reaction. The heat removal part has been taken care by the coolant pump. So here in the fast breeder reactor, we use sodium, it's a liquid metallic sodium as a coolant. It's a very good, it has very good thermal conductivity, very good hydraulic properties, whereas it is highly reactive with water and air. When it reacts with water, it generates heat and also it generates hydrogen. Hydrogen may be used, is required for the country for moving from one fuel to another, but hydrogen is very much not required for the nuclear reactor, because hydrogen has a capability to explode the complete vessel, then the radioactive decay can be easily reach the environment. So since it is generating the heat, it means it is getting, it catches fire, since that has a hint to us, so that we can implement certain methodology to monitor whether any sodium leak or sodium related discrepancies are happening inside the reactor. So we have a three broader applicability of the modeling that we have and has been used in different places of inside the nuclear reactor. The first one, the fire detection model. So fire detection is the general model that we developed, and it can be deployed for sodium leak detection. Since when the sodium leaks to the environment, it reacts with the air, catches fire, generates hydrogen. So that fire can be detected, so that leak detection can be identified. So currently, the leak detection has been doing with contact-based sensors, whereas with this technology, we can go for non-contact-based methodology. So, and then the hydrogen deflagration is an event which happens during the sodium disposal scenario, where when the hydrogen started catching fire. So we wanted to see that particular event. If that event happens, we have to turn off or take mitigation during the sodium disposal plant. So the hydrogen deflagration happens in less than a half second. So we used to have a high resolution and high-speed camera imaging to capture that event. So we use a normal fire detection model using CNN, and we can use a segmentation model for, we are using segmentation model for the hydrogen deflagration with high throughput rate. So on general scenario, we can implement this model for fire breakout scenario throughout the industry, throughout the plant. So and then we predominantly use a sequence modeling technique, since we are dealing with sensor data. The sensor data we have to analyze based on the sequence of patterns. So we use for sensor data analytics, we use this modeling, and then identifying the pattern recognition. Even when there is a video, for example, if you want to detect hydrogen deflagration event, it's going to be the second step in detecting that event, because it is a sequence of frames, we have to detect it. So and then video analytics purpose, currently we are not using it right now, but it can be extended for monitoring purpose. So, and then the reinforcement learning, this one we predominantly use almost in all of our systems where we have an automation control. So whenever we wanted to control, let's say if I want to control a pump, if I want to control a temperature controller, I can use this reinforcement learning technique. It is based on reward and penalty based method. So it can be used in autonomous robots, and then we are currently using in the process optimization, and then even fine-tuning the parameters of the PID controllers. So the deployment strategies. So the deployment strategies can be easily related to an analogy of an story. Let's say there are two friends who are traveling in a bus. So one of them has bought two tickets instead of one for him. So the another one was surprised and asked why you bought a duplicate ticket. He told, what if in case if I miss one ticket? And then another friend got frustrated and asked him, what if he missed both of them? Then I have already a bus pass which is renewed every month. So it seems to be a funny story, but this is, he is true in case of an uncertain environment where the reliability has been given the more preference. So the exact same methodology, we use it for deploying any models which is going directly to the production. We use sensor data, we just take the sensor data and develop a machine learning model, let's say model A, and then we deploy it in the hardware unit, let's say hardware 1, and then I go for redundant deployment. So I'll be having same sensor data, and then I'll be having the same model, model A, but I'll be deploying it in a different hardware unit. It's not the different core, it's a different hardware unit separated out from the first board. So this one we can relate it to what is meant by the duplicate ticket. So, and then the diversified deployment will be having a different data source with same sensor, maybe different sensors of different technology. Let's say if I wanted to measure temperature, the first one uses thermocouples, then I'll be using in the diversified deployment. If I have transmitter-based pressure transducer, or else then I'll be using piezoelectric-based transducer in this particular diversified deployment, so that if one technology or one technique fails, the another will capture the particular event. So, and then we go for a completely different model. So we will not use, for example, if I use a model A, let's say as a random forest, I cannot use this random forest in the model B. I have to use a completely different architecture. For example, it may not be decision tree as well. I have to go for even deep learning models or something like that. So, and then I'll be deploying it in a different hardware. The hardware also needs to be as much as different as possible. For example, the hardware 1 and 2 follow some architecture, the hardware 3 should be from a different architecture. So, for example, if I want to develop an end-to-end machine learning system, if I want to deploy that system, I'll be having a ton of workload just for the same output and for the same input. I'll be having different models and different deployment strategies to be used, and we'll be having a final decision logic. It will take, whether if it is classification based on the majority vote, or then if it is regression based, it averages out the results. And finally, since there are no tolerance of error in the nuclear reactor deployment, so we need to have the system, the decision making system has to be highly interpretable. So currently we are working on explainable AI techniques, where the models which is not explainable by themselves, we have to apply Lime or Shapely. Thanks for that. And we are using such models to identify how the decision has been taken with a model, example in the CNN and other models. That's about for the talk today. Thank you. Thank you, Cypher, for this wonderful opportunity.